All right, so today I'm gonna be explaining a very important but very old paper in 2009 from this UAI conference. This is a very old paper, but it's very inspiring. It sheds light and it gives you insight to how to generalize this score matching. Is this the end of score matching, or you can generalize it in many different aspects? For example, this is not related to this paper, but what if you combine energy-based methods with score matching? The energy has the real absolute truth. Like in molecular dynamics, you have access to energy. And in score functions has the gradient of P. You don't know P, but have some approximation of the gradient of that. And there are some papers like energy matching and many. Another direction is that we can, this is this paper that I will explain it. So score matching is a recently developed parameter learning method that is particularly effective to complicated high-dimensional density models with intractable partition functions. In this paper, we studied two issues that have not been completely resolved for score matching. First, we provide a formal link between maximum likelihood and score matching. Our analysis shows that score matching finds model parameters that are more robust with noisy training data. Second, the second one is very important. We develop a generalization of score matching. So, score matching is a different parameter learning methodology. And first by Hivarian, this Finnish guy in 2005. And now, formally, we can say it's the Fisher divergence between P and Q. Q theta, it has theta, it means that we want to learn it. P doesn't have theta, it means it's absolute truth. But we don't know. So this gradient is the gradient operated with regard to x. And the learning procedure that finds theta to minimize this Fisher, this F is Fisher divergence between two probability. And so just the KL divergence is induced from Shannon divergence entropy. So does the Fisher divergence from Fisher information. So this integration by parts is very simple, but it helps us a lot. You know, in test functions, in functional analysis, we multiply both. For example, if you have a PDE, for example, you have a strange PDE, then you multiply the left-hand side, the right-hand side with a test function. Then you integrate by part, then you have a better integral representation of that. That is very fruitful. Here they used this integration by parts, the last term in 4. If you use 5, then it ensures this boundary value vanishes. At the boundary, the value vanishes. So score matching and maximum likelihood, there is a striking similarity between Fisher divergence and KL divergence. Because if we rewrite the Fisher divergence like this, their difference lie in that instead of using the likelihood ratio, the Fisher divergence compute the L2 norm of the gradient of the likelihood ratio. And this implies that there may be a deeper relation between them. In the appendix, they have proved this lemma that for any positive valued function whose gradient and Laplacian are well defined, we have this relationship. The proof is very simple. We just use the definition of Laplacian. Then this lemma is interesting, the heat kernel lemma. And so again, applying integration by parts, the limits at the boundary values are all zero due to smoothness and fast decay properties of P tilde. So theorem 1, this theorem that relates this d by t of KL to the Fisher divergence. You relate KL divergence to Fisher divergence. It reveals some intriguing aspects of the relation between score matching and maximum likelihood by setting up a formal relation between Fisher divergence and KL divergence. So this is the outline of this paper. That this is very interesting. But what is generalized score matching? The score matching learning can be generalized to more flexible parametric learning methodologies, starting with definition of Fisher divergence. The main idea is to replace the gradient, which is a linear operator in density functions, with a general linear operator. So if X has discrete components, integration is substituted with summation. We turn this DL, the generalized Fisher divergence, and this one, the generalized core function. So if a functional is a very general thing, is much more general than just gradient. So that's why they take advantage of this idea, and we can have a generalized core function. So a linear operator, we say, is complete if for two densities, then this is equal. If this holds, then they are equal. And here they talk about marginalization. By the way, the previous two videos that I talked about concrete score matching, their method, I noticed that it's just a particular marginalization. Marginalization is very general. Of course, we can think about more general than this, but marginalization is very general. Integration is to be replaced with summation when X hat is has discrete components. Like in language, like in graphs, everything is discrete, so we don't integrate with sum. And here they talk about generalized score matching for discrete data. So whenever we say discrete data, it means it can be tabular data. You can apply it for language. You can apply it for graph, and etc. So consider this discrete vectors like C1, C2, Cm, and with density P of X. The integration in equation 12 is replaced with summation. So we have now summation. And this is the equivalent of that functional that I said we have integral of them. Now we have summation of this. Then if we substituting the equation 15 and using dummy variables, these TCIs are dummy variables, we need to marginalize over the i's component of X hat in the inner integral. So dropping the first term that is independent of theta, we have this. Then after simplification leads to this one. And this Q is just the conditional probability for the ith element, but not taking value KCI. Also, it has a relation with ratio matching.